thank you for supporting our job creation for astrophysics program. It's wonderful to be here. I'm looking forward to a really good day of discussion about some really interesting projects, which I found myself involved in by complete accident about 10 years ago now. I study things like the image that's on the center here. I study galaxies, systems of stars, dust, gas, dark matter that make up the building blocks of the universe. And one of the things I care about is how we got the mix of galaxies that we see around us today. One way to quantify that is to look at the morphology of the galaxy. The shape of the galaxy tells you about its history. It tells you about how it's interacted with other galaxies. This is in fact a picture of two galaxies which are about to undergo over the next billion years or so a rather radical change in shape. And so classifying galaxies by shape is something astronomers have done since at least the 1920s. And initially it was the preserve of learned professors who would write books on galaxy classification schemes. When we got to the 1980s, we got thousands of images of galaxies that were worth classifying. It was discovered that graduate students could classify galaxies, and the task was farmed out to PhD students. But by the time we got to about the year 2000, we had surveys of millions of galaxies. And by experiment, I know that you can't get a grad student to classify that many galaxies. The experiment's name was Kevin Shawinski. He looked at 50,000 of these images before he decided he'd had enough, and demonstrated along the way, by the way, that this was a task that was better done by humans than computers. More on which later. So I tried buying Kevin beer. That didn't work. And so without really thinking about it, we created a website called Galaxy Zoo. This is what web design looked like in 2007, for those who don't remember it, frames and everything, which gave you a random image of a galaxy and asked the simplest question that was useful. We asked whether this was a spiral galaxy or an elliptical galaxy, or a merging galaxy or a star. And then we asked which way, if it was a spiral galaxy, we asked which way the arms were turning. And the response surprised us. I expected this site to appeal to amateur astronomers. We thought we'd go and talk to local groups of people with telescopes who do astronomy for fun, and we thought maybe 50 people at a time would do 50 to 100 classifications, and we estimated that in 5 years we'd get through our million galaxies. What happened instead was that the site was picked up online, it was featured on the BBC News, and we found a huge crowd of people, most of whom had never been interested in astronomy before, and most of whom didn't have astronomy as part of their daily lives, were quite excited about the opportunity to contribute to scientific research, to spend a few minutes doing something useful. It's the phrase that kept turning up in the surveys. And so within a day we were doing 70,000 classifications an hour, and over the last 10 years Galaxy Zoo has done 300 million classifications. And taken collectively, we have no problem with the accuracy. Because we have lots of people looking at each galaxy, we can get not only a classification, but an understanding of how much we should believe that classification. And the results are great. I don't really have time to talk you through any more galactic astrophysics, but I did want to highlight this is a paper by a researcher called David Watson. This is I don't believe in citation indices unless they agree with me, but the bar chart here is the average number of the percentile, so it's the ranking of Galaxy Zoo papers amongst other astronomy papers, and the bell curve there, the Gaussian, is the average citation rate of papers using the same data. So by taking the same images and putting them through citizen science, by getting volunteers to add value, we've created some very valuable science. The next thing that happened was that people started calling us and saying, people with data who had the idea that people who were interested in galaxies might help out with their data sets. So this, for example, is nothing to do with astronomy. This is a remotely triggered camera on part of the Antarctic Peninsula. It's placed there by my friend Tom, who studies penguins for a living. He used to go to these places once a year and count the penguins. So they had an annual census. These days, this camera takes an image every 2 minutes. And when Tom turns up once a year, he takes the memory card out and comes back to Oxford with about 30 million images of penguins every year. But there's still only one penguinologist. There's still Tom and maybe his PhD student. And so if you get an image like this, you need to understand how many penguins are in this image. So it's early. We can do some crowdsourcing. How many penguins are in this image? 3? Interesting. I gave this talk to computer scientists last week, and 2.4 was the consensus there. but I think 3 is the right answer. So you're clearly good at this. Let's warm up. Just shout when you've counted the penguins.
But it's the best thing to do if you're on conference call.
That's true, yeah. yeah, exactly.
On the conference call and you click on them.
Yeah, but maybe not this image. But the point here is that the correct answer is too many. And as I suspect you all refuse to count these. And so you have that human ability to detect when a task isn't useful and to do something else, a way that a machine learning routine wouldn't do. Anyway, the site we created is called Penguin Watch. More than 30 million penguins have been counted. This is it in action. The original name for this site was Penguin Hunters, but apparently that didn't go down well with the biologists. You can still see some traces of that thinking there. But nonetheless, this is one of what is now a large set of projects that live within what's called the Zooniverse, which is a platform for this sort of distributed data analysis of images, of text. We have some text transcription projects looking at things like 16th century documents or the Tate's collection of artist notebooks. We've got some audio projects and some video projects. And actually we've gone one step further. As of last year, you can build your own Zooniverse project without knowing any web development. So if you go to the laboratory section of the website, you get this interface, which is a very easy route to creating one of these projects. So it's absolutely free, and people can come along and create their own projects. I have a colleague who at this point in talks likes to demonstrate that he can build a project in 90 seconds. We think on average it takes people about an hour and a half to go from nothing to a project that's worth showing to our community. And the effect of this project builder is obvious. Here's the number of Zooniverse projects over time. See, we took a while to recover from the shock of Galaxy Zoo, and then we built a variety of different projects, and then last year we get this step change as people launch more projects. So these projects produce science, but that's not the interesting thing about them. I think it's a necessary thing, but that's not the interesting thing. What's interesting are the people who are participating, the 1.5 million people or so who are registered with the Zooniverse. So what happens to them when they encounter these projects? We know, I've already told you, that these aren't people who are already science fans. These aren't people who, when they visit Manchester with their family, make a point of coming to museums like this. Nor are they science phobic. These aren't people who actively campaign against mitigating climate change, for example. They're the kind of people who, if they're reading the Metro and there's a science story, would read it. But they wouldn't buy New Scientist. Well, one thing we know is that they learn stuff. So we did a recent survey where we tested the scientific knowledge of participants using a set of images. And the top set of images here were used to test people's general scientific knowledge. Do you know what these images are? And then we used other sets of images to test specific knowledge in the domains of different projects. The middle set was used to test Galaxy Zoo knowledge. The bottom set, the knowledge of volunteers in a project called Snapshot Serengeti, which is looking at motion-sensitive cameras in the Serengeti. And the result, which is in this online open access paper, is that even if you control for the general science knowledge that people come into a project with, they learn about the area of science with which they're engaged. So these projects are vehicles to learning. Actually, I think they're better than that. When we've done surveys, we find that people learn things that we don't even tell them. The knowledge that we were testing, say in the Galaxy Zoo test here, wasn't necessary knowledge for classifying these galaxies. It was the context, the astrophysics, the cosmology that surrounds it. And so what's happening is this project is acting as an engine of motivation. Participation in the project makes you want to learn about the subject with which you're engaged. So that makes that very effective science communication. And it can be taken to extremes. Here, for example, is a result from a project called Planet Hunters. Planet Hunters literally has discovered more than 100 planets around stars other than the sun. And you look for them by looking for a blink. So you have a graph of brightness. This is one star's brightness over the course of about 3 years. And where you see a dip, something has got in front of the star. And most of the time you see a regular pattern of dips, and that's a nice planet on a nice round orbit. our planet hunters identified this star, KIC 8462852, for those taking notes, who they called it the WTF Star, where WTF stands for Where's the Flux? Because as you can see, or at least that's what we told the journal editor, as you can see, there's this very irregular pattern of dips that make no sense. The star lost 20% of its light. There are lots of explanations put forward for this thing, which tends to be known as the most mysterious star in the universe. Some explanations are more sensible than others. This is the result from colleagues in the States who said that maybe this was caused by an alien megastructure around the star. I'll emphasize that I'm showing the Independent because they at least use the word may. But what's nice about this is the paper discussing this features citizen scientists as authors. And in particular, Darrell, who's the second author here, was the person who spotted that there was something interesting about this star and said you should pay attention to this, and actually did a lot of the basic work to quantify what was happening. And then he collaborated with this very long list of professional astronomers who had their own expertise to throw in to the paper. So people like Darrell, and we see this happening in lots of our projects, go from not being interested in astronomy to being engaged through sort of click work, through the basic tasks that they're set, to discussing what's going on, to participating within the full community of scientists. So it's tempting to put these into a hierarchy, and there's some great work by Carsten Oosterlund at Syracuse and Kevin Crouston, his colleague there, which sort of you could sort of start to think of a hierarchy of tasks here. And I suspect we'll see some of this in Muki's presentation as well, where you go from just clicking to generating your own labels, to talking about what you're doing, to doing analysis. And as you move from one to the other, you find yourself going from working on your own to working in a community. So that's exciting, especially because we were able to show, at least from a survey, that there's no relationship between how far up this hierarchy you go and many of the things that you bring with you when you join the project. So there's no relation to age, to gender, and in particular, there's no relation to how much science knowledge you bring in. So that we're not filtering, right? It's not that there's a small community within this broader community who are doing advanced stuff, who are the people with science degrees, sitting at jobs in the city being bored or whatever. We actually really are taking people from an entry level of no interest in science and not a science background to the point where they're contributing to papers, though we're only doing that for a small number of people. So this is very exciting, and one is tempted, I think, to think of the stuff at the top of this hierarchy as the real citizen science. That if you take the citizen in citizen science seriously, then what we want is an engaged community of citizens who are driving the research agenda, who are making their own choices about what we should be working on, and who are indeed given all the tools and facilities and opportunities and affordances that they need to do their own research and talk to those of us who get paid to do this for a living as equals. And that's a nice picture to have. I'd love to live in that world. But the problem we find is that that's not a vision shared by the people who come into our website. For example, placing the word citizen science on the front page of a Zooniverse project in the strapline reduces participation by a factor of about 6 because it's an aspirational label. For starters, you have to think of yourself as a citizen, as an active participant. And secondly, you have to think of yourself as a scientist. And the general reaction to me introducing myself to anyone is that, oh, I was never any good at that at school. And so we're immediately putting that barrier in front of people. And one thing I wanted to talk about today was to propose an analogy to the museum world. Here's the front of the National Gallery. It's obviously an imposing sort of imperialist building. It's designed to show off that our country has an amazing collection of art and by extension is an amazing place. It's designed to give you a sense of importance, which if you're somebody who's a member of the National Gallery or somebody who's a regular visitor, that's a good thing. You feel that you are being lifted up by being inside the gallery. However, there's a concept in the museum world called threshold fear. And the idea is that you won't go over this threshold unless you already think of yourself as somebody who will get something out of being in a gallery. And I think in science we have this in spades. People won't aspire to be citizen scientists until the point at which they see themselves as able to get something out of being involved in a science project. And so there are two solutions to that. One is costly. We know there are great projects, several of them represented in this room, that break down that barrier through sustained community engagement. But it's hard to do that on a scale of 1.5 million people. On the other hand, what we think we've got here is that the small tasks act as the thing that gets you over the threshold. You fall into a Zooniverse project after following a link on Facebook without ever making a conscious decision to care about galaxies. And then if you see something interesting, we see people being motivated, then they care to learn about galaxies. And so the order is almost the reverse of a standing teaching environment. We want you to do stuff, and then we'll worry about giving you the opportunities to do more. So I see the micro tasks as essential to the success of these projects. And there's a threat on the horizon. The threat looks something like this, in that the robots are coming. Machine learning, deep learning, computer vision have made enormous strides in the last few years. And so it's certainly possible that in many of the kind of projects we do today, that you could hand large sections of the data analysis to robots, leaving only the small leftover portion, the difficult stuff, for humans. In fact, in many cases, we want to do that because the amount of data that we're getting is ever increasing. And if we don't share the load with our robot colleagues, we're going to deeply suffer. And we're not going to be able to get the best out of the data set. We want to reserve human attention for the truly unusual rather than the routine. We've started doing that. We've built systems that combine human and machine classifications in lots of these projects. And we can show with real data that the combination of human and machine outperforms just having machines. But it comes with a cost, which is a change to the volunteer experience. I want to finish by giving you a specific example. These are images from Snapshot Serengeti, the motion-sensitive camera trap that I showed you. On the right, you've got some exciting images. This is a lion. I can tell that as an astronomer. This is some sort of stripy horse. I'm not an expert on all the projects. And on the left are more typical images. It turns out about 70% of the images that these cameras capture are blank. And they fire because there's something in the distance moved, or in case of the bottom left, what happens is the grassland heats up, and as the winds blow, the grass waves, and you take many, many pictures of grass. And if you care about animals, this is a waste. It's also an easy machine learning problem. So we can recognize with off-the-shelf routines and the training data we've already got from volunteers, with easily greater than 95% accuracy, the blank images. And so we can remove them from the project. That's good. Our volunteers tell us they want to make a real contribution to science. Therefore, we shouldn't waste their time. Therefore, if we can get rid of these blank images, people could be more effective, they can contribute more to science, and they see more exciting images. Except that when we've done it, participation drops dramatically. And what's happening is that we've changed the experience. We've gone from nothing, 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 zebra, to zebra, zebra, wildebeest, zebra. It's much less exciting, and you don't get the sense of adventure and exploration. So that creates an ethical problem. We could just throw the blank images back in, but we're telling people that we want to do this for science. And we know we don't need them to classify the blank images. It's not clear how we resolve that and how we talk to our community about that. What we really need to do, I think, is as we optimize these systems, as we start to build systems that dynamically assign tasks between human and machine, that start to pay attention to who the experts in the crowd are so that they get the more interesting or more difficult images. We need to be able to measure not just how accurate our knowledge about an image is, we need to understand from the data how interesting an image is. We need to understand how likely that image is to promote learning. What's disturbing about this question is that the commercial companies who control traffic on the internet and give you your news feed and so on know one thing. There's a huge amount of work in detecting what will make you look at the next thing. So we can optimize for sustained engagement. We've played this game too. We have a model that predicts with 70% accuracy when somebody's about to stop. And we could, although we don't, give you a particularly exciting image at that point. But optimizing for learning is a whole nother kettle of fish. It's a much more difficult problem. And understanding how to do that while preserving the micro task element of these projects, which gets people over the threshold, is a really difficult problem. I hope some of you will be able to help and will enjoy discussing that today. Thank you very much.